about soils. I can't remember how many of you came to that, but I've put it up because the sort of underlying issues are described here about how soils are structured, and the pore size distribution is absolutely key to what makes soils different, and therefore why we need to go to the bother of calculating SEVs. And the main advantage of SEV, why we do it, is because it is designed to be a number that's transferable between soil types. So in Lawrence's case, if you're working entirely on Nuba and the soil's reasonably uniform, then just doing water table depth, should be fine. But if you then go up to Sefton or something and it's a different type of sand, then water table depth will mean something different, and certain SEVs are supposed to smooth out those soil-based differences. So we just talk through soil hydraulic properties and the fact that they were based on both texture and structure, and that you can, structure is not a permanent thing, it can collapse as a result of compaction. So you can't even assume the same site will always be the same if the soil gets damaged. And how water's held in soil. So saturation's fairly easy to understand, all the pore space is water filled. Field capacity is what soils can hold against gravitational force. So if the soil can drain, you'll get some air spaces developing, but there's still a lot of water in there. And then permanent wilting point is when the plant can get more water out, but there is still water in there. So the moisture content of a soil can still be quite high, even when a plant can extract no more water from it. In a sand, that would be very low. That would only be 5% or less, but in a clay it can be 40%. So your soil is still 40% water by weight, but the plant can't extract anything because it's bound too tightly. And that was to make the point of just how different soils can be in terms of how they hold water, that sands have a big drainable porosity, so their water tables tend to move quite slowly because such a large proportion of the soil is water. So you have to evaporate a lot to drop the water table by 10 centimetres, whilst in a clay, especially a poorly structured clay, you evaporate very little and drop the water table by 10 centimetres. So on that graph, the drainable porosity of that clay is about 4%. That's the height of the blue column, whilst the drainable porosity of the sandy loam is not far off 20%. So if you have, during a week, you may lose 2 centimetres of water through evaporation. On the sand, that would cause water table to drop by 10 centimetres. On the clay, would cause water table to drop by 45 centimetres. So this is why you can't, water table depths are not comparable across soils because they behave very differently. And this diagram also shows the importance of structure in terms of how much water is available to the plant. On the sand, it's very small because nearly all water drains away, leaving little available water. On the poorly structured loam, it's small because water doesn't drain away, but most of it's held so tightly the plant can't get it. but it's the well-structured clay loam that has the big available water. So it's doesn't subject plants to so much stress as the other two would.